This is Precalculus Lesson 7, Graphs of Polynomials, coming from Section 2.2 in the College Algebra textbook, and this is Ruth Trigstead. We're going to start with the definition of a polynomial function, which is a function of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 2 x squared plus a sub 1 x plus a naught, where a naught through a sub n are real numbers and n is a non-negative integer. The domain of a polynomial function is all real numbers, as we've already talked about a bit. And let's go ahead and look at some functions and determine which of these are polynomials, starting with f of x equals 4x to the fourth plus 9 minus 13x squared. We can rewrite f of x in descending order as 4x to the fourth minus 13x squared plus 9. And in either form, f of x is a polynomial. We note that the coefficients of 4 and negative 13 are real numbers, and that the exponents here are non-negative integers. The only thing that you might notice is that we're missing the x cubed term and the x term. Well, if we think of those terms as having a coefficient of 0, then we can pretend like they're there, and this is definitely a polynomial function. So let's go on to g of x, which is equal to 2x squared plus 7 square root x plus 2/3. I will rewrite this function as 2x squared plus 7 times x raised to the power of 1/2 plus 2/3. Now we have a problem, because note that the exponent on the x of 1/2 is not an integer, and so g of x would not be a polynomial because we have an exponent that is not an integer on one of the x terms. So going on to h of x equals 3x cubed plus pi x minus 2 over x. Let's rewrite this function as 3x cubed plus pi x minus 2 times 1 over x, or 2 times x raised to the power of negative 1. Well, the x here with an exponent of negative 1, that's a problem, because negative 1 is not non-negative. In order to be a polynomial function, we would need only non-negative integer exponents. And so h of x is not a polynomial. However, I want to point out before we go on that we have pi as a coefficient on the x here. And actually that presents no problems at all, because pi is a real number. So it meets the criteria for being a coefficient on the x. Anyway, let's go on and look at some characteristics of polynomials, including degree, leading term, leading coefficient, and constant term. As an example, we have f of x equals 4x to the fifth plus 9x to the fourth minus 13x squared plus x minus 7. The degree of this polynomial function is the highest power of the variable that appears in the polynomial. So we can see the highest power of x is the fifth power. Our degree is 5 here. The leading term of f is the term containing the highest power, so we just grab 4x to the fifth as our leading term, and then we look for the leading coefficient, which is the coefficient of the leading term. We can see right here that that's 4. Finally, the constant term is the term with no variable. So we can see that the negative 7 here at the end, this would be like plus negative 7. There is no variable with the negative 7, and so our constant term here would be negative 7. Moving on, let's look at g of x equals 2. This doesn't look like the type of polynomial function we're used to, but in fact it is a polynomial function if you think of this as being 2 times x raised to the power of 0. Then its degree would be 0. Its leading term, there is only one term, so that would be 2. The leading coefficient, again, would be 2. The constant term, since 2 is a constant, the constant term is 2 as well. This polynomial function h of x is a little more complicated looking, and it's not clear as to where we find the leading term from. So let's think of h of x as being equal to negative 3x plus 0 times 2x plus 3 cubed times x minus 2 squared. Now we have three binomials, each raised to a different power. So if I want to find the leading term here, what I can do is I can take the highest power term in each of these three binomials and raise it to the corresponding exponent on that binomial. So we would have, in that case, negative 3x raised to the power of 1, 2x cubed, and x squared. This simplifies to negative 3x times 8x cubed times x squared. Negative 3 times 8 is negative 24. We add together the exponents and the x's, 1 plus 3 plus 2, and we get negative 24x to the 6th as our leading term. I'll show you by actually expanding h of x in a couple minutes here exactly how we can show that this is the correct answer for the leading term. And now the degree of this polynomial function. Well, the leading term gives us a degree of 6. The leading coefficient here would be negative 24. Then we look for the constant term. Okay, again, we need to mess a little bit here. So going up above to where, let me erase a few things here. Okay, so for the constant term, I'm going to look at each of these three binomials that we have up above, and we are going to take the constant term from each of these, raise each of these constant terms to the power associated with that binomial, and multiply them together. So we would have 0 raised to the first power times 3 raised to the third power times negative 2 raised to the second power. 0 times anything is 0, so we find here that we do have a constant term of 0. And to verify the leading and the constant terms here, let's go ahead and expand this polynomial. And we'll start by writing 2x plus 3 cubed as 2x plus 3 times 2x plus 3 times 2x plus 3. X minus 2 squared we'll write as x minus 2 times x minus 2. And then I'm going to multiply 2x plus 3 times 2x plus 3 and x minus 2 times x minus 2 to give us 4x squared plus 12x plus 9 and x squared minus 4x plus 4. Then I'll go ahead and multiply 2x plus 3 times 4x squared plus 12x plus 9. And we keep going. Next, we have two polynomials here that we're going to multiply together. And I'm not going through all the steps here because it would take way too long, I think. So try this on your own. Finally, we're going to distribute negative 3x through, and we get h of x is equal to negative 24x to the 6th as our leading term, plus some other stuff. And then at the end here, we have plus 0. And so we can see that it is true that our leading term is negative 24x to the 6th. Our constant term is 0. The intermediate value theorem is our next task of the day. Suppose f is a continuous function on an interval containing x equals a and x equals b with a less than b. I have a graph here that we're going to use to figure out what's going on here. So we have x equals a somewhere here and x equals b with a less than b. The other things we're being careful of is that f of a and f of b have different signs. So if you look here, if we plot the point a, f of a on our graph, f of a is negative. If I plot the point b, f of b on my graph, f of b is positive. So f of a and f of b have different signs. And what we're told here, if this is the case, then f has at least one zero between x equals a and x equals b. That is, for at least one real number c such that a is less than c is less than b, we have f of c equals 0. You can see such a point does exist here. There is a point c such that f of c equals 0. If we want to look a little closer at what's going on here, I'm going to start by drawing a coordinate system with an x and y axis, and I'm going to put a point a, f of a on here, where f of a is positive in this case, and I'm going to put a point b, f of b on here, where f of b is negative. So f of b and f of a have different signs. So what I want to ask you, is it possible for a continuous function to pass through a f of a and b f of b and not cross through that x-axis? I don't see where that would be possible with a continuous function. So somehow or other, if we have a continuous function, we're going to have to pass through the x-axis at least one time. In this case, what I've drawn here, we would have 1, 2, 3, it looks like 4 places between x equals a and x equals b where we would have an x-intercept or a 0 at those points. So we're going to use the intermediate value theorem next to show that, oh, I missed one little, let me go back a sec. I missed making a note that polynomials are always continuous. So polynomial functions are continuous everywhere on their graphs. That's why the intermediate value theorem is nice to have right now when we're working with polynomial functions. And we're going to next use that theorem to show that f of x equals x cubed minus 2x squared minus 5x plus 5 has a real 0 in the interval from 0 to 2. So in this case, the 0 is going to be our a, the 2 is going to be our b. So let's see what we need to show. First of all, we need to show that f is continuous. Well, f of x is a polynomial here, and so it has to be true that f of x is continuous on all intervals, including 0, 2. The next thing for the intermediate value theorem is we need to find what f of a is, in this case f of 0. So f of 0 is equal to 0 squared minus 2 times, let me backtrack, 0 cubed minus 2 times 0 squared minus 5 times 0 plus 5, which simplifies to 5. We next find f of b, which is f of 2 here. And that would be equal to 2 cubed minus 2 times 2 squared minus 5 times 2 plus 5, which simplifies to 8 minus 8 minus 10 plus 5, or negative 5. Okay, looking good. Since f is a continuous function, and since f of 0, which is equal to 5, is greater than 0, and f of 2, which is equal to negative 5, is less than 0, then by the intermediate value theorem, f has at least one 0 in the interval 0, 2. Now, try on your own. Use the intermediate value theorem to show that h of x equals x raised to the power of 1000 minus x minus 3 has a real 0 in the interval from 0 to 2. This is similar to what we just did, but this one's going to take some thinking on your part to see why this would be the case. And so as you're solving this, write down your notes to yourself, your explanation on why this does work. Let's go on then to graphing end behavior of f of x equals a times x to the n, where n is even. And we'll look at a graph of y equals x squared here. So let's just call this f of x equals x squared. And for f of x equals x squared, we notice that 2, the power on x, is even. And we also note that a, which would be 1 here, is greater than 0. So let's see what the end behavior is like for this particular function. So as we're approaching negative infinity for x values, as we go to the left in the x direction, our graph goes up, right? So So as we go left, our graph goes up. What happens as we go to the right? As we go right, our graph also goes up. Okay, so to write this in mathematical notation, what we would say is as x approaches negative infinity, as we're going to the left, f of x approaches positive infinity, goes up. As x approaches positive infinity, or goes to the right, f of x approaches positive infinity or goes up. If we want to look at the case where a is less than 0, let's just reflect f of x equals x squared about the x-axis so that we have, let's call this g of x equals negative x squared. So what's going on with g of x equals negative x squared? Well, if we look at the end behavior, as we go to the left, then our graph is going down. So here, as our x values continue to the left, our graph goes down. Same thing happens to the right. As we go to the right, again, our graph goes down. We would write this as x approaches negative infinity, going to the left, g of x approaches negative infinity, and as x approaches positive infinity, going to the right, g of x approaches negative infinity as well. Looking at the other case here, where we have f of x equals a times x to the n, and n is odd, let's look at a graph of f of x equals x cubed. Here we note that a, which would be 1 here, is greater than 0. Let's look at the end behavior. So as we go to the left, our graph goes down. As we go to the right, our graph goes up. Or as x approaches negative infinity, f of x approaches negative infinity, and as x approaches positive infinity, or goes to the right, f of x approaches positive infinity. Okay. Flipping this graph across the x-axis, we have g of x equals negative x cubed. Okay, for g of x equals negative x cubed, we still have n is odd, but here a, which would be equal to negative 1, is less than 0. What's happening with n behavior as we go to the left, our graph goes up. As we go to the right, our graph goes down. And we would write that as x approaches negative infinity, g of x approaches positive infinity. As x approaches positive infinity, g of x approaches negative infinity. Moving on, we want to describe the end behavior of f of x equals 2x cubed plus x minus 5. So we're going to use what we just looked at. For f of x, the highest power term, or the leading term here, is going to give us our end behavior. And so for our end behavior, it would be like y equals 2x cubed. And notice that we have an odd exponent on the x. We have a positive number here for 2. And so our end behavior is going to be similar to that of y equals x cubed. It helps to just kind of sketch the graph here to remind you of what the end behavior is. And that would be as we go left, or I'm not going to do the technical language here. We just need to know for graphing purposes at this point, although I want you to know how to use technical language. As we go left, our graph goes down. As we go right, our graph goes up. All right, and then let's try g of x equals negative 2x to the fourth minus x squared plus 1. The leading term here is negative 2x to the fourth. And so we have a negative here, a negative coefficient on the x to the fourth, and 4 is an even integer. And so we're going to resemble the end behavior of y equals negative x squared, like so. Again, there could be all kinds of stuff going on here in the middle, but our end behavior of this function is going to be the same as the end behavior of negative x squared. So as we go left, the graph goes down. As we go right, again, the graph goes down. Or you could say the y values decrease. Okay, moving on to here, the end behavior. This is one of those where, let's see, we have to figure out what's going on here with the leading term. So the leading term would be, we have 2x times x minus 3 cubed times 2x plus 1 squared. So we can take 2x raised to the power of 1 times, for x minus 3 cubed, we have the binomial x minus 3. The leading term there would be x. We take x raised to the third power. For 2x plus 1, I take 2x, raise it to the second power. So we have 2x times x cubed times 4x squared, or 8x raised to the 1 plus 3 plus 2, the sixth power. So we have a positive 8. We have an even power on x for our leading term here. Our end behavior will be like that of y equals x squared. So as we go left, our graph goes up. As we go right, our graph goes up. Okay, now multiplicities. These are another important thing we need to know when we're graphing polynomials. So f of x equals x squared times x plus 1 times x minus 2 cubed. We want to find the zeros and their multiplicities. So think about, if I set f of x equal to 0, what would be my solutions to setting f of x equals to 0? Well, we could start by looking at what if x equals 0. That would cause this function to be 0, or it would cause the y values here to be 0. So 1, 0 is x equals 0. What if I set x plus 1 equal to 0? Well, I get x equals negative 1 is a 0. And what if I set x minus 2 equal to 0? I get x equals 2 as a 0. So I have zeros of 0, negative 1, and 2. What are the multiplicities of these zeros? I look at the factor from which I got the zeros, and I look at the power that that factor is raised to. So with x equals 0, the multiplicity would be 2. X equals negative 1 came from x plus 1 being raised to the first power. So the multiplicity is that power 1. X equals 2 came from x minus 2, which is raised to the third power here. So our multiplicity is 3. Now to sketch a rough graph of this function, we have our zeros of negative 1 with multiplicity 1, 0 with multiplicity 2, and 2 with multiplicity 3. Now we want to look at the end behavior. So let's real quickly see if for the end behavior, what would the leading term be? It would be x squared times x raised to the first power times x raised to the third power. So the end behavior would be like x to the 6th. So that's a positive x raised to an even power. The end behavior would be like y equals x squared. So as we go left, we go up, and as we go right, we also go up. Okay, one more thing here. I want to look for the y-intercept. So for the y-intercept, we would set x equal to 0 up here. Setting x equal to 0, we would have y equals 0 squared times 0 plus 1 times 0 minus 2 cubed. Well, 0 times anything is just going to be 0. And so we would get a y-intercept of 0, 0. Now let's try to plot this information that we have. So starting with zeros of -1. Okay, so right here we have a 0 of -1. We have a 0 of 0. This is also the y-intercept. We have a 0 of 2. That means where we have a 0, we're going to be crossing the x-axis, as long as they're real zeros, I should say. Our multiplicities, we don't have any other y-intercepts. There's only this one at 0, 0. In the next problem we do, we'll see that the y-intercept can help us with graphing. In this one, we need to totally depend on the end behavior here to help us graph. So I'm going to start on the right side. On the right side, we're going up. So we're going to, right here we have x equals 2. From there, we're going to be heading up. So what happens at x equals 2? Well, the multiplicity tells us whether our graph crosses or touches at each of these intersects. So an odd multiplicity, like we have with x equals -1 and x equals 2, tells me the graph is going to cross the x-axis. An even multiplicity, like we have at x equals 0, an even multiplicity of 2, tells us the graph is simply going to touch and bounce at that point. So right here, we've started our graph at x equals 2 here. We're going to cross the x-axis, and then we're going to travel backwards in this case to where we have x equals 0, where we're going to simply touch and bounce. Finally, at x equals -1, our graph is going to cross. Whoa, I kind of messed that one up. Okay, let me try that again. That's not great, but it kind of works. Okay, it's hard to draw on the vertical here. So we have a rough graph. Notice this says rough. It's not a perfect graph. What I want to use my graph for is I want to know where the graph is above the x-axis, where it's below the x-axis, and where it touches or crosses the x-axis. Also, I want to know what the y-intercepts are, which I want to know where it crosses the y-axis, and that's it. I don't really need any more information for these rough graphs. Let's try another one here of g of x equals -3 times x minus 2 times 2x plus 1 squared. We'll start by looking for zeros and then multiplicities. So by setting g of x equal to 0 here, we would start by our first factor here is -3. I set -3 equal to 0. It's not going to give me, any results really, because there's no way -3 is ever going to be equal to 0. So I move on to x minus 2. If I set x minus 2 equal to 0, I get x equals 2. So my first 0 is 2. We notice that x minus 2, the factor from which I got that 0, is raised to the power of 1, giving me a multiplicity of 1 here. And then we look at 2x plus 1 squared. If I set 2x plus 1 equal to 0, I'm going to get x equals -1/2. So we have a second 0 of -1/2. The multiplicity on that 0 would be 2. Okay, the other things we look for are end behavior. So our end behavior, if we take -3 times x raised to the first power times 2x raised to the second power, I have negative 3x times 4x squared, or negative 12x raised to the power of 3. So we have an odd and a negative here. Our end behavior is going to be like y equals negative x cubed, something like so. Think of reflecting y equals x cubed across, or did I mess that up? I think I might have I messed that up, okay. So I didn't reflect. Okay. So if we reflected, this would be y equals a negative x cubed. Okay, so this would give us our end behavior. As we go left, the graph goes up. As we go right, the graph goes down. Finally, let's look for a y-intercept. To find the y-intercept, we would set x equal to 0. So looking back up here at our function, we would have y equals negative 3 times 0 minus 2 times 2 times 0 plus 1 squared, or negative 3 times negative 2 times 1, I think. So we're going to have a y-intercept of 0, 6. I'm going to start here by plotting the y-intercept of 0, 6, and then we have a 0 at x equals 2, and we have a 0 at x equals negative 1/2. From our multiplicities, 1 is an odd multiplicity, so the graph is going to cross at x equals 2, and x equals negative 1/2 has an even multiplicity, tells me the graph is going to simply touch at that point at x equals negative 1/2. Okay, so with a y-intercept, I don't have to use end behavior to graph, but it's a good check. So let's kind of start at at the point 0, 6 on the y-axis, and if I go backwards to negative 1/2, I'm going to simply touch at that point. So something like so. If I go to the right then, to x equals 2, my graph is going to cross there. And so we have that general behavior of this graph. Notice we don't know whether from on the y-axis at the point 0, 6, we don't know if the graph goes above or below to the right. We don't really know what's going on there. We just know our x and y intercepts. We know where the graph is above and below the x-axis, and from there it should give us some information that we need for other things along the way. So let's go ahead next and do the try on your own number 2 for today. Sketch a rough graph of the function f of x equals 2x times x minus 2 squared times x plus 2. And one more thing I want to do today. I want to create a polynomial p with the following characteristics. This is number 26 out of the textbook. So I want a polynomial that has, for which the solutions to p of x equals 0 are x equals plus or minus 3, x equals negative 2, and x equals 4. Okay, so let's kind of start with that. So I want a polynomial p of x, which is equal to, so we're going to have some factors going on here. So if my solutions to p of x equals 0 are, let's start with x equals 3. So if x equals 3 is a solution to p of x equals 0, then that tells me that x minus 3 equals 0, from which I can get the factor x minus 3. We're kind of thinking backwards from what we were doing earlier. Before we were starting with x minus 3, and it was telling us we had a 0 of 3. Now let's go on to x equals negative 3. If x equals to negative 3, then x plus 3 equals 0. So this tells me I have a factor of x plus 3. Then x equals negative 2 would give me a factor of x plus 2. x equals 4 would give me a factor of x minus 4. Okay, so let's see. We've got the first step here taken care of. Now I want to make sure the leading term is negative x to the 5th. Okay, well, we might have some number here stuck out in front, so I'm just going to throw in a for now. The big issue I see here is having a power of 5, because right now I have a power of 4. So one more bullet point here tells me that the point negative 2, 0 is the local maximum on the graph of y equals p of x. So if I was graphing this function, and I have the point negative 2, 0 right here, we can see that negative 2 is a solution. It's a solution of p of x equals 0, or it's an x-intercept. When y equals 0, we get x equals negative 2. So this particular point on our graph is going to be a local maximum, which means our graph right here is going to look something like that. Well, what does a local maximum tell me? It tells me that the graph is going to bounce or touch and bounce at that point, and that the power of the factor giving me that x equals negative 2 is going to have to be raised to an even power. Here I'm going to choose a power of 2 to give me 1, 2, 3, 4, 5, to give me x to the 5th. Okay, the other thing we need to take care of, though, is that the leading term has a negative, that it's negative x to the 5th. So we need to figure out what a is. So I want to end up with a leading term. What would my leading term here be? From what we've been doing, the leading term would be a times x raised to the first power times x raised to the first power times x raised to the second power times x raised to the first power. So my leading term would be a times x raised to the 5th power, and we want the leading term to be negative x to the 5th. Well, that just tells me that a is going to have to be equal to negative 1, so I can finish off with my polynomial. It's going to be negative 1, or just negative of x minus 3 times x plus 3 times x plus 2 squared times x minus 4. And here we have it. All right, well, as always, ask me if you have questions about anything, and hopefully this lesson goes well for you.